This is now entering the second half, and I think what you'll realize is that this half, the half you already did, is was much conceptually more difficult than what you're about to encounter. And the reason being that it's really, we're going to do the same things again and again and again. So the first half of the class exposes you to a bunch of novel ideas. The eminent, or the most core idea that we encountered is this use of marginal trade-offs to characterize optimal decisions, right? So a consumer was faced with this consumption problem, and the optimal decision often, not excluding corner solutions and such, the optimal decision was often characterized by a marginal consideration that giving up a little bit of X in exchange for Y is exactly equal to the price of giving up a little bit of X in exchange for Y, right? That the marginal rate of substitution was equal to this ratio of prices. And the marginal rate of substitution is a marginal consideration. What we're going to see now is that those same marginal considerations are going to establish optima in the production side of the economy. So really, all of the intuitions that we already built are still there. In the same way that when we moved from utility maximization to cost minimization, there was sort of like it felt almost like we already did it. You had to kind of understand the intuition of how you go from one problem to another, but for the most part, it's already there. So we're going to see that entire thing now, the whole chunk, gets moved over into production. All the intuitions sort of carry over. It's more of a translation process than learning something totally new. And I actually think it's a little bit easier to begin with. So that's cool. So right now we're going to talk about production. So this is the other side of the economy, right? This is the supply side. How do firms decide how much of a quantity of a good to produce, or sometimes how do they choose which goods to produce? And what does it mean to produce goods? It means you have to hire inputs. Inputs can be technology. Inputs can be other intermediate goods. Inputs could be like raw material. Inputs could be labor. And they're going to turn that into some output that they're going to sell in a market at some price or whatever. And of course, in real life, firms do tons and tons and tons of other stuff. So real firms do research and development, trying to create new technologies, make their technologies more efficient, change their cost structures. They give to charity. They do marketing and advertisement. They feud with other firms. They have all sorts of financial goals that they uncover, and they I don't know, do other stuff too, probably, that I'm not even thinking about. Of course, just like in the consumption side where we said a consumer is just a utility function, here we're really going to think of a firm as just a technology. And what I mean by a technology is a method of turning inputs into outputs. So, I'll be precise about this in a couple of slides, but the idea is that we're abstracting away from all the other things. So just like before, when we said, we're going to zero in on one very small, maybe kind of silly component of the consumption process, here we're going to zone in on one very small, potentially silly aspect of being a firm, and that's just turning inputs into outputs. So you could think of a firm as just a machine, and the machine just takes, capital and labor, or it takes computers and computer coders, or it takes tractors and laborers, and it just turns that into wheat or Apple products or whatever. And so this has the added benefit of allowing us to be very specific about our assumptions, turn them into math, and then use that math to make predictions that are very general, right? Of course, if you really care about the way that firms interact, say, in the charity sector, or how they interact with higher education or something like that, hiring interns, or how they influence policy or whatever, then you're going to have to add that into your model, and that's going to be potentially completely throw off everything we've done, right? So what we're talking about now is very specific. It's general in a certain sense that it applies to any firm, but there could be gum in the works, right? If you really wanted to move towards a more complicated or more realistic model. So for now, actually probably the entire time in the class, we're going to assume that firms just hire two inputs. Capital, which starts with a K in economics, because C was already taken for cost. So C is going to be a cost function. Costs are somehow more primitive than capital, so capital starts with a K. Actually, this also might come from German. In German is capital with a K, and maybe someone wrote it. I don't know. Doesn't really matter. We use K for capital and L for labor. L makes sense for labor because there actually is an L at the beginning of that word. And we're going to think of a single output, which is going to be denoted by Q, which is the quantity produced. And almost everything we're going to talk about will go through without a hitch, with just very minor adjustment if you wanted more inputs or you wanted more outputs, right? So a firm could, instead of producing one output, baseball bats, they could produce two outputs, hockey sticks and baseball bats, and then they would just adjust the levels, the relative levels, and their production would be a vector instead of being in specific real number, right? And you could have the input have three inputs. They could be capital, labor, and some intermediary good, wood or something like that. So I hire, machines to turn the wood into baseball bats. I buy the wood itself, and I hire someone to, activate the machine. This would have an extra input. Nothing really is going to change about anything, right? The idea of trade-offs between different goods is the same as it was in consumption. We almost always just dealt with the trade-off between two goods because extending it to three goods is the same. Just pairwise, everything holds the way it holds with two goods. So you have more first-order conditions, but other than that, nothing really changes. So a production function is therefore just a function from R2 to R. So F, our production function, takes a vector in R2. This really should be R2 plus, just positive real vectors. And what is R2 plus? It represents, it's a two-dimensional vector. Right? It's a vector with two real numbers, positive real numbers. And what do those represent? The amount of capital hired and the amount of labor hired. So it's a vector K and L, where K and L are real numbers. K is the amount of capital and L is the amount of labor. And it returns a single real number, and that single real number represents the amount of the output that's produced, the quantity of the output produced. And this should seem very familiar, right? We wrote down over and over again utility functions that took R2 to R. And in a lot of ways, there's an analogy between this, right? You're taking inputs and you're creating an output. Here, the output is physical. Before, the output was some metaphorical utility. And in fact, that makes our life a lot easier because if I go to a firm, I can examine through its accounting how much capital it's hiring, how much labor it's hiring, and then I can just figure out how many baseball bats it sells, and from that I can conclude the actual production function, or at least parts of the actual production function, right? The production function is theoretically observable. It's not like utility, which was based on some metaphor that was on top of this preference relation or this idea of binary choice. A production function's a physical thing. It's how you literally combine inputs, capital and labor, how, it's a tractor and a guy driving a tractor, and how much ground they can cover and how much wheat they can produce with their tractor. That is a physical thing. It's an observable thing that you can go out and you could study. And that means that, we can say a lot more about production than we could have said about utility functions. Because utility functions were anything that we were able to say had to be ordinal, right? Remember that we couldn't talk about cardinal properties of utility, something like convexity, because convexity didn't actually arise from any kind of component on this underlying preference structure. I could take a monotone transformation of a utility function and I would have the same preferences. I would have the same underlying behavior, and it wouldn't change anything about the maximization process. Here, with a production function, we could talk about convexity, right? Convexity is a totally reasonable thing to talk about because it just says, if you double all the inputs or something, you more than double or whatever. I mean, that's not exactly what convexity is, but you have two vectors of inputs and you take some common combination, you're producing more or less than the common combination of the outputs. That is a totally reasonable thing that you could go out and study and ask that question and answer that question by observation. There's nothing particularly difficult about it other than, tracking down how farmers and tractors produce with each other. And so there's a lot more of a reasonable sense in which we can talk about specific properties of production functions and have them be meaningful than we could have with utility functions. So one particular example should be familiar to all of us. It's the good old Cobb-Douglas production function, right? So we had Cobb-Douglas utility functions. Why not make a Cobb-Douglas production function that says that the quantity produced when you hire K worth of capital and L worth of labor is some exponentially related thing, K to the alpha, L to the beta, where alpha and beta can be shown, we'll talk about later what this means exactly, are proportional to capital and labor's share of the output, right? So that's how important are they to the output process. If beta is equal to 1 minus alpha, so if alpha and beta sum up to 1, then capital owners would receive alpha percent of profit, and labor owners would receive, or laborers themselves would receive 1 minus alpha percentage of profit. This comes into like the macro literature of, the distribution of profits towards, the capital ownership versus the labor ownership in this general equilibrium models, which I'm sure you're studying in your macro class, so maybe that looks familiar. And we're going to study the micro properties of this, but of course at the macro level, one might care in society how much of the relative profits go to laborers, and you could estimate this alphas and betas theoretically. But of course, there's a lot of simplifications going into any kind of actual empirical estimation, so take it with a grain of salt. But that's the idea, is that you could estimate these things and come up with actual reasonable estimates for alpha and beta based on how much of the profit is going from one to the other. So given a fixed amount of capital, we could ask how much does each unit of labor contribute to the output on average, right? And that would be called the average productivity of labor. And it should say, and likewise, the average productivity of capital, right? There's a copy and paste error on the slide. But the idea is that you have an average productivity that's just the average, right? It's the total production divided by the quantity of labor that's hired for a fixed K. The average productivity of capital for a fixed L is the total amount of capital divided by the total amount of production divided by the total amount of capital. Likewise, we can define the marginal productivity of labor, and that's the derivative of the production function with respect to labor at a fixed amount of capital. And likewise, the marginal productivity of capital is the derivative of the production function with respect to capital, right? So this is how much does the marginal, does increasing your labor supply by a tiny fraction. And remember that these are indivisible goods. So I'm not going to be as detailed about going through all the places where we make assumptions as I was in the first half, because I assume that we sort of are carrying over those kind of considerations and thinking through them ourselves, rather than me just telling you, this is a problem, this is a problem, this is a problem. But I'll point them out when they come up. Here, we're assuming that labor can be hired in infinitesimal units and capital can be hired in infinitesimal units. This is actually not so unreasonable, because you could think of labor as being a time thing. How much time are you hiring a laborer for? Rather than thinking of it as hiring another full-time person, which would be in discrete units. With capital, maybe you're also renting time on a machine, something like that. So the marginal productivity of labor says if I just increase my labor supply by a tiny, tiny amount, proportionally, how much does my total production change? And the same with capital. So if I had a wheat field, I'm a farm, I'm the landed gentry in England, and I own this wheat field, and I can hire some fixed amount of labor and capital. At that particular point of labor and capital, the average productivity of labor is how much wheat is grown per farmhand. I just add up all the wheat. I say I collected 8,000 bushels of wheat, and I had 4 farmers or something. That means, on average, each one was contributing, well, I already forgot which number I said, but the total amount divided by 4, I think it was 2,000 bushels of wheat per farmer. Right? The marginal productivity would say, if I hired this guy for a little bit extra, how much extra wheat would I get? Right? So conceivably, if I have a wheat field with no farmers on it, and I hire one farmer, I'm going to get a lot of wheat compared to what I had if I had no farmers, which was 0. If I hire a second one, it's not necessarily that I would get the same amount back, which means that the marginal productivity might be changing as I hire more or less people. And of course, the average productivity would then change as well. In fact, the average productivity is highest when the average productivity is equal to the marginal productivity. So this is a theorem. You should be able to convince yourself of this pretty quickly. The idea is if I hire one more laborer and they contribute more than the average, then the average is going to go up when I hire them, right? So if the average is currently 3,000 bushels per person, and I hire someone and they produce, their marginal contribution is 4,000 bushels, then the average has just increased. right? Likewise, if I hire people and the next guy contributes less than 3,000 bushels, then the average will decrease, which means that in order for the average productivity to be at its highest, means that it's increasing and then decreasing, right? It means that the marginal productivity has to be exactly equal to the average productivity, right? Because if it was any higher, it'd be increasing the average productivity. If it was any lower, it'd be decreasing. And we want, right? Think about the derivative of average productivity. It has to be flat. The average productivity has to not change if it's at a local maximum. So local maximums of average productivity are where the average productivity is equal to the marginal productivity. You can prove that using the algebraic relations on first order conditions if you feel inclined. And maybe that will be a homework question. In most, and it's hard pressed to think of anything where this is not the case, marginal productivity is eventually decreasing. We can't just keep adding farmhands and expect to grow more wheat. Eventually, they're going to crowd each other out, right? Eventually, we're going to have a couple of acres. I don't even know. Do you use acres in English? In England English? Obviously, it's an English word. I think they came from England. I'm going to go ahead and say, yeah, you use acres. Not that you can answer since I'm talking through a video, but you have some fixed area of land, and you hire the first farmhand, and they can run the tractor, they can start harvesting wheat. You add another one, they're working in tandem. They can each do the thing that they're better at. One guy's good at driving the tractor, one guy's good at irrigation. They're doing great. You hire a third guy. Now he's not as helpful as the second guy. He's kind of like, he's just doing the leftover jobs. You hire a fourth guy, he's got almost nothing to do. He's just sitting there. You hire a fifth guy, and he starts bumping around into people, and it's actually like you're barely doing anything better than with four people. The sixth guy, in fact, is hurting you now, right? The sixth guy is just like in the way. He's standing in front of the tractor. The tractor's trying to run him over, and he's like, he can't get out of the way because there's no room because it's a small piece of land. And in pretty much every scenario, if you just kept adding things into a set factory or whatever, there's just no room, right? There's like a technological constraint that eventually adding more technology or adding more inputs is going to decrease the actual production. So marginal product is eventually decreasing. Often it's eventually negative. Basically the idea is that the other inputs get overwhelmed, right? There's not enough of the other stuff to compensate for the extra labor or for the extra tractors. Now, you could say, well, maybe you could add more tractors and stuff like that. So we're talking about marginal productivity with a fixing the other inputs, right? And also, eventually, you run out of the other inputs or whatever. So we'll talk more about this at a larger, maybe higher up philosophical level in the seminars. I think it's not, this video is already getting kind of long. So let me end with a couple of examples. The first one is just a production function, 30 k squared L squared, k to the third minus k to the third L to the third. We'll assume for now that capital is fixed and equals 1. So you have one tractor, so k is 1 in this equation, which means that the production function is just as a function of L, right? So we're a fixed amount of capital. You can't change it at the moment, right? It takes a while to order a tractor or something like that. Which means that you can hire more laborers, and your production as a function of how many laborers you have is just 30 L squared minus L to the third. The marginal productivity of labor is just the derivative of F, which here is equal to Q. F is the function, Q is the output of the function. The derivative of F with respect to L is just 60L minus 3L squared, and that eventually decreases. In fact, it is eventually negative, right? So the maximum production is when the marginal productivity is equal to 0, right? So, I mean, if we're just, that's just a first order condition, right? You're saying I'm trying to make Q as big as I can. That's occurs when the marginal productivity goes from being positive to becoming negative. And so that happens when the first derivative of Q with respect to the choice variable, in this case L, is equal to 0. And that's going to happen when L is equal to 20, right? That's just setting this third bullet point equal to 0. You get Is that right? So that'd be 400, 400, 600, 14. Yeah, I think that's right. 60 times 20 is 1200, right? And then 3 times 400 is 1200. Cool. Sorry. It's been a while since I looked at the slides. They are correct. The average productivity of labor is just the production function divided by the amount of labor hired. And that would just be 30L minus L squared, right? So that's just this second bullet point divided by L. And we could ask, where's the highest maximum average production for a fixed K? And that's when the derivative of the average productivity of labor is equal to L, is equal to 0. And that's, you can take the derivative of that first line, you get 30 minus 2L, that's equal to 0 at 15. So that means that the highest average productivity is when you have 15 laborers. But in fact, you want to continue to hire laborers here if you're trying to maximize the quantity produced. You're still getting more production out of each additional laborer until the marginal productivity becomes 0, right? So the average productivity will fall between 15 and 20, but it will not, your quantity produced will not fall. So of course, there's no reason why a firm would want to maximize quantity produced. That's not necessarily the correct thing to think about. We're just saying if you were looking at that, that's what's happening here. I'm not saying that that's the goal of a firm. We'll talk about the goals of the firm in a little bit. So don't worry. If you're worried, stop worrying. All right, that's enough for now.